Have you ever played billiards before? If so, you might have noticed the many types of collision that can happen in the game. During the start, a player will use the cue stick to strike the break shot, scattering the billiard balls all over the pool table. Sometimes the shooter will hit the cue ball right on the middle to do a stop shot. Doing this, the white ball would abruptly stop after hitting one of the eight balls. Most often, the cue ball will be struck off center, causing an angle shot, in order to pocket a ball in a rather awkward position. Collisions that happen in billiards, baseball, or vehicular accidents are all governed by the same law of physics, the law of momentum conservation. But before I state what it says, let me tell you more about the two types of collisions. Collisions can either be elastic or inelastic. To show you how the two collisions would look like, let's take a look at this simulation. This one is elastic collision. We have two balls of equal mass that are moving towards each other at the same speed. The sum of their kinetic energy is 0.37 joules. After the two balls hit each other in elastic collision, they fly away at opposite direction at the same speed, and the kinetic energy remains the same, 0.37 joules. But what if inelastic collision happen involving the same balls? The two balls will stick together after the collision, and the kinetic energy will be reduced to zero. Elastic collision or bouncy collision happens when there is no loss in net kinetic energy in the system before and after the collision. By system, we mean the blue and the pink balls. If the sum of the kinetic energies between the two before collision is 10 joules, then the sum stays the same afterwards. In an elastic collision, some of the kinetic energy of the system is lost in the form of heat or sound. Of course, the direction and the speed of the two objects after collision also depends on their mass and initial velocities. To prove this, we are going to look at three different simulations. In the first one, the blue is double the mass of the pink one, but both are moving at the same speed. We can see that after the collision, the blue ball moves slower while the pink ball became faster. The kinetic energy remains the same, 0.56 joules. In the second one, both have the same mass, but the blue ball is moving twice as fast as the pink ball. After the collision, the pink ball comes faster than the blue ball, but the kinetic energy still remains the same. In the last one, blue ball is twice as big and twice as fast as the pink ball. After the collision, the blue ball stopped, like a stop shot in billiards, while the pink ball was catapulted to the opposite direction. Then let's take a look at what would happen in these settings if the collision is inelastic rather than elastic. What is noticeable is that in elastic collision, energy of the system is just transferred between the two balls, it- with the slower or lighter ball getting it or seen moving faster after the collision. Meanwhile, in inelastic collision, objects tend to stick together after the collision with noticeable loss in speed and kinetic energy. In real life, perfectly elastic collision is difficult to observe. Collisions in billiards and Newton's cradle give us a glimpse of how this can happen. Most collisions we see are inelastic. A ball made to bounce on the floor will not bounce back to the same height. A mud flung to the wall will stick to it rather than bounce back. In the nursery rhyme, if Jack fell down and collided with Jill, they would go down the hill together. But what is common between the two types of collision is that whether elastic or inelastic, the total momentum of the system before and after collision is conserved or stays the same. This is true as long as no external force is present, like for example, friction or air resistance, which would slow down the motion of two colliding objects. Here's how elastic and inelastic collision inside the spaceship will look like. Inside, no air resistance is felt and the pull of Earth's gravity is very weak. If we treat this truck and the car as a system, the truck having a mass of 3,000 kilogram and moving at 10 meter per second towards a 1,000 kilogram car that is at rest. The total momentum is 30,000 kilogram meter per second before collision. After the collision, the truck moved at a lesser speed of 5 meter per second, while the car was propelled forward at 15 meter per second. The total momentum of the system is still 30,000 kilogram meter per second after the collision. Another example is the total momentum of a baseball and the catcher's mitt after, before and after the catch. Before the collision, only the incoming baseball contribute to the total momentum of the system, as the glove is stationary. After the collision, both objects stick together or move as one. However, the total momentum stays the same. But how is the law of momentum conservation observed in more complicated situations, such as an explosion? Before an explosion, the total momentum of a dynamite is zero since it is stationary. After the explosion, the dynamite breaks into thousands of pieces going off in all directions. The sum of all the individual momentum is said to cancel out each other, making the total momentum after the explosion still equal to zero.